Assalamualaikum and hello everyone. My name is Nur Hazatul Salwa binti Cik Hasan from AS 2713321. In this video, I will be presenting a summary of Chapter 2 and Chapter 3 for PHY568 Electromagnetic Theory. Although these are two separate chapters, they are actually closely related. Chapter 2 introduces the mathematical tools used to describe vector and vector fields, while Chapter 3 applies those two to explain electrostatic phenomena such as electric field, electric potential, and Gauss law. Before we begin, this slide provides a brief overview of today's presentation. I will first explain the fundamental concept introduced in Chapter 2, followed by Chapter 3, where these concepts are applied to explain electrostatic phenomena. As we go through the presentation, you will notice how the ideas from Chapter 2 are continuously used throughout Chapter 3. Let's begin with vector fundamentals. In physics, we distinguish between scalars and vector. A scalar only has magnitudes such as mass, energy, and electric potential. In contrast, a vector has both magnitude and direction. Examples include force, displacement, and electric field. Once we understand vector, we can perform several basic operations. For example, vector addition combines two or more vectors to obtain the resultant vector. The dot product produces a scalar and is commonly used when calculating work or determining the angle between vectors. Cross product is an operation between two vectors that give another vector as the result. It can be calculated using the determinant method. We also can calculate vector magnitude to determine size of a vector in both two-dimensional or three-dimensional space. Finally, vector operations obey the basic algebraic laws such as commutative, associative, and distributive law, making vector calculation more systematic. Now that we have learned about the vector, the next question is how do we represent them in space? This is where coordinate system become more important. The Cartesian coordinate system is the most familiar one and mainly used for rectangular geometry. When dealing with circular objects such as wires or cylinders, the cylindrical coordinate system becomes more convenient. For objects with spherical symmetry such as charged sphere, we use the spherical coordinate system. Choosing the appropriate system makes the mathematical calculation much simpler and more convenient. After representing vector, we now need mathematical tools to analyze how vector fields behave. This is the purpose of vector calculus. The gradient describes the direction in which a scalar quantity increases most rapidly. In electromagnetic, it closely related to electric potential. The divergence tells us whether a vector field is spreading outward or converging inward at a particular point. The curl measures the rotational behavior of vector fields. Another important operator is the Laplacian, which appear in many electromagnetic equations involving electric potential. Finally, important theorems such as divergence theorem and Stokes theorem allow us to convert between different types of integral, making many electromagnetic problems easier to solve. This concept will become especially useful in Chapter 3. Now let's move on to Chapter 3, where we apply the mathematical concept we just learned. The first topic is Coulomb's law, which describes the electrostatic between two stationary point charges. According to Coulomb's law, the force is directly proportional to product of the two charges and inversely proportional to the square of distance between them. It also explains why like charges repel while unlike charges attract. Instead of only focusing on the force between charges, we introduce the concept of the electric field intensity represented by E. The electric field describes the force experienced by a unit positive test charge placed at a particular location. Since the electric field is a vector quantity, it has both magnitude and direction. The field points away from positive charge and toward negative charge. In a situation, electric charge is not always concentrated at a single point. Instead, it can be distributed continuously along a line, over a surface, or throughout a volume. They are known as line charge density, surface charge density, and volume charge density. Another important concept is electric flux density, represented by D. It describes the amount of electric flux density passing through a unit area. Understanding charge distribution and electric flux is essential because they provide the basis for applying Gauss law, which is the next topic. Gauss law establishes the relationship between the total electric flux passing through a closed surface and the total charge enclosed within that surface. It can be expressed in two forms. The integral form considers the total electric flux through an entire closed surface. Meanwhile, the differential form describes the behavior of the electric field at a single point. One major advantage of Gauss' law is that it greatly simplifies electric fields calculation for highly symmetrical charge distribution. For example, it is commonly used two-point charge, infinite line charge, infinite sheet, and spherical charge distribution, where selecting an appropriate Gaussian surface makes the calculation much easier than applying Coulomb's law directly. Finally, let's look at electric potential and current density. Electric potential represents the amount of work required to move a unit positive charge from infinity to a specific point in an electric field. It is closely related to electric field through the equation E equal to negative gradient of V, showing that the electric field points in the direction where the potential decreases most rapidly. Current density, represented by J, describes the amount of electric current flowing through a unit cross-sectional area. In conclusion, Chapter 2 provides the mathematical foundation through a vector analysis, while Chapter 3 applies this concept to explain electric charge, electric field, and electrostatic phenomena. Together, this chapter builds the fundamental knowledge required for understanding electromagnetism. That concludes my presentation. Thank you for your time and attention. I hope this presentation has provided a clear understanding of the key concept in Chapter 2 and Chapter 3. Thank you.